Hi, welcome to my course on Microsoft Virtual Academy, which is building recommendation systems in Azure. I'm Olivia Kloser. I am a technical evangelist based in Munich for Microsoft Germany, and I'm mostly focusing on Azure data insights such as HD Insight, Azure Machine Learning, Stream Analytics, and so on and so forth. This MVA course is structured in 5 modules. We start off with the typical introductory module called Machine Learning and Recommenders. The typical things such as, hey, what is machine learning? When is machine learning good? What do I do to do a machine learning problem, and so on and so forth. And then obviously focusing more on recommendation problems. This first module will then be followed by targeted marketing. Well, after the first module, we will go through certain scenarios and we'll show you demos as well that you can do at home yourself. The third one is collaborative filtering, one of the 2 main approaches in recommendation engines, and therefore closely followed by the other main approach in recommender engines, which is called content-based filtering. This MVA course is then rounded up with a final module called Azure Marketplace, especially for those of interest who want to have recommenders implemented in their website or in their app and so on and so forth, but can't be really bothered to actually learn about machine learning or can't be bothered to build those machine learning models. So for those people, we actually have an offering as well in the Azure Marketplace where you can just acquire your plugin. Just to set the right expectations. So the target audience of this MVA course are the typical developers, BI analysts, data professionals, and yes, data scientists as well. Although data scientists probably know all about recommenders already, it might be interesting to see what we from Microsoft actually offer in terms of tooling that you can use in your day-to-day work. Suggested prerequisites would be linear algebra analysis and statistics. Doesn't mean if you don't know any of it or can't really recall what you've learned at high school or at university, don't worry. The whole point of Azure Machine Learning is to democratize machine learning anyways. So let's get started with the first module, Machine Learning and Recommenders. This module is structured in a way that we first start off with machine learning scenarios, then why machine learning, when to use machine learning, and then finally digging deeper into what is actually of interest to us in this particular course, which is recommender systems. So everyone knows handwritings are very special, very specific to every single person. I don't know about you, but I certainly cannot read what this person might have actually written there. What it actually was is referred. I could have never judged that or never known that this actually means referred. But you can see handwriting recognition is very complex. Yeah, sure, you can think of all sorts of rules, but then there's bound to be the 1001st person that pretty much just exceeds all their rules, or is not, or whose handwriting is not covered by the 1,000 or by the set of 1,000 rules, for instance. So this is actually one example where machine learning is used, and not just theoretically or in the academic sense, but also it's been used in the postal service. So I think up to the 2000s or something, everything has been done more manual. Nowadays, if you send a letter or a postcard, yes, I know we are in the age of internet, but from time to time you do send postcards as well. Nowadays, all the addresses are being processed via some machine learning algorithm and has been optimized from year to year. So you can see that machine learning is a very iterative process. It's not here you've got all the data, learn everything, and that's it. You've learned everything straight at the first instance. No, it's a life or almost a lifelong process. So I often compare this also to little children as they grow up. Obviously, if when they are 3 years old, they don't learn everything straight ahead. They still observe everything, and then based on what they have observed, what they have seen, what the feedback was, they then learn as well. So one colleague of mine, for instance, has told me about his 3-year-old son who just came by his office and said like, "Hey, oldie, what's up?" And then obviously my colleague wasn't really that happy about it because he's not that old. He doesn't like to be called old. So obviously he told his son, "Hey, son, you shouldn't call me oldie. You can call your mom oldie," for instance. So his son then registered, okay, got the feedback, shouldn't call my father or shouldn't call my dad an oldie anymore, but maybe I can try it out on my mom. So you see, it's a lifelong process. We are still learning. So an iterative process, which is also the case here. I think it has taken up to like more than 10 years to optimize more and more those algorithms to automatically recognize handwriting. So with machine learning, you see or you hear a lot of buzzwords as well. The typical ones are descriptive analytics and diagnostic analytics, which is more about, this is traditional BI, traditional business intelligence. This is what happened. Why did it happen? What actually happened? Once we enter the area of machine learning or data science, it's actually getting more and more interesting. This is what we call advanced analytics. So the typical buzzwords here are predictive analytics and prescriptive analytics. Here, typically, or just imagine you have your factory, you have all your machinery, and you want to know what the probability or which part of this machine is going to fail within the next 2 weeks at a probability of 80%, for instance. And then prescriptive analytics is to optimize your current setting in a way that, how can we make it happen? So obviously, with machine learning being a very popular buzzword at the moment, what actually is machine learning? And there are many definitions. One, I think, very good definition is the following. The goal of machine learning is to program computers to use example data or past experience to solve a given problem. I think the two keywords or two key expressions here are either example data or past experience. Yeah, sure. With machine learning, there's always this misconception that you're predicting the future. So why do you need historic data? And therefore, it's very important. You need past experience or historical data to do calculations, and based on those calculations, make predictions, for instance. And with make predictions, what we actually mean is calculate probabilities of something actually happening. If you don't have historical data, but example data, so you want to somewhat understand first what data you have, and therefore you can do some clustering. But first of all, you need to start with data. Some four rules that you can use when to actually apply machine learning are these ones. I mean, they cover the basics, but obviously there are always some special cases where you need to take other factors into consideration. But the 4 key rules would be something like, if you have a problem that is very complex, as in you can't really code it. And one typical example for this is handwriting recognition. Sure, you can set all sorts of rules as well, but this is such a complex problem that there's bound to be another person that isn't covered, or whose handwriting is not covered by all the rules that we have already set. Another rule would be if you have too much data, if you can't scale it. So, for instance, a spam detection or fraud detection, there's just so much data that you always have to keep on learning and have to automate the learning process as well. Another example for using or for applying machine learning would be if it's too specialized. nowadays the customer is key, or wants to feel like royalty. Obviously, I don't want to feel like someone who has the very same taste. I want to have my very own preferences, and therefore everything is all about personalized recommendations, which is very interesting to us, especially in this course anyways. So typical examples would be Amazon, Netflix. So based on what you've watched so far, we recommend you that. But yeah, I'll go more into detail with Netflix in a few minutes anyways. And then another typical scenario when to apply machine learning would be if it's all about autonomy, like doing something autonomous, if you can't track it. So AI gaming or having your robot armies play football against each other. Just very recently, there's one very good blog post by one of our data scientists, and he has this is part of a blog series, how to trying to demystify data science. So what do I actually need for data science? If I think I actually have a data science problem, how do I check if that is actually the case? So for starters, you need to actually have a very well-defined question or business objective. Something like, I want to know what I should do on Monday is extremely vague and is not well-defined at all. A very well-defined question would be, which of my machines, or is this part of my machine going to fail within the next 2 weeks? Or to what probability would it fail within the next 2 weeks? So this is one part, actually defining the business objective. The other part is obviously the data that I've mentioned beforehand. There's no point in doing machine learning if you don't have any data. And machine learning or data science is often, it's often taken synonymously with big data. Sure, big data and machine learning are overlapping, but are not the same. With big data, we always talk about petabytes of data. Here with machine learning, we talk about smaller data, but the relevant data. So more about gigabyte of data, I would say. And with data, we want to have the relevant data. We want to actually have the data that is relevant to our business objective. There's no point of having data of people who might call in sick during certain days, which might affect our machines and the factory, because these are two completely different criteria, very independent of each other. Then we want to have, if we have relevant data, we want to have it as accurate as possible. There's often this misconception thinking that, hey, okay, if I even have messy data or not very accurate data, I can make it up with lots of data. That is wrong. You can only have a very good algorithm or a very good machine learning model if you have the relevant data, which is also accurate. And then the next point with connected data, what my colleague means by connected data is, you want to have all those different data sources, but these have to be somewhat connected to each other. They have to be mapped to each other. Well, there's one point of having all this data of people walking along a shopping mall, but and then it's another thing if you have a data set on like some loyalty program, but it's much more of value if these are connected, knowing that this person has actually been going from this shop to another shop and so on and so forth. And then the final one is, I did say that big data is not, or machine learning is not necessarily big data. But there's no point if you have, let's say 1,000 data rows to do a machine learning problem, because it would be too specific. We need more data, and therefore here large data is necessary. So it sounds like it's still a lot of statistics or a lot of BI. What has changed? Why is suddenly machine learning or data science such a big buzz? And I think it's more about, evolution-wise or history-wise. So far, or the main challenges with data science is, first of all, you need skilled data scientists, which usually have a PhD in maths or statistics or computer science and so on. But then they are the hyped unicorns nowadays, because you don't only think that they have a perfect statistics background, they can hack their way through, but they also have the best business understanding as well, or domain knowledge. So this is one main challenge as well with finding those unicorns. And I'm more of the opinion that data science is more of a collaborative and iterative process, working together, like a statistician or a computer scientist working together with someone from the domain. The challenges so far have also been infrastructure. Well, it's getting cheaper and cheaper to store data as well. Compute is now being more and more outsourced in the cloud as well, and therefore you can just scale it. And then also the next one with time. So before I joined Microsoft, I studied machine learning in the medical imaging area, and there I remember running my algorithms. It just takes so long until I finally get some results. Thanks to the cloud, thanks to the Azure platform, we can just accelerate this process and find out which parameters, which algorithms work best in certain scenarios as well. And then obviously the final one, well, once data scientists have found their perfect model, how do they scale this? How do they scale this globally, as well as, deploy this within minutes to certain applications? And this is where Azure Machine Learning is quite useful. So we've covered some basics of machine learning, and let's get more into detail with recommendations. And as I mentioned before, and one of the examples, number one, that you can think of straight ahead is Netflix, if you think of recommender engines, or as well as Amazon. But I think Netflix is very interesting from 2 points of view. One story is, so I'm a huge fan of the series called House of Cards. And the background story of House of Cards is really interesting, because what Netflix did is Netflix has a lot of data on their users. They don't only know which movies you've seen, which series you've seen, but they also know which series you've seen, like within what time. If you've seen 4 episodes of one series within one night, this is a good indicator that you actually really, really like this, that you really like the series. So yeah, they've crunched the data, and then they also realized, most of our users or subscribers actually like the miniseries, the original miniseries of BBC called House of Cards. They are also huge fans of movies where Kevin Spacey is the main actor, and huge fans of movies directed by David Fincher. So they just added 1 and 1 together and realized, hey, okay, this is the perfect combination. So they approached Kevin Spacey and David Fincher and said, hey, we've done our data crunching. We trust in you, and therefore here you have $100 million, and just produce as much as you'd like, or just go ahead. They just did their big bets on House of Cards, thinking that, hey, there's no need on doing a pilot episode first. Just go ahead. And therefore, they just went ahead with 2 seasons straight away. This was a huge success for Netflix itself. Another interesting aspect is also, yeah, sure, with Netflix, you get a lot of recommendations, what movies you might watch, which series you can watch. And according to one blog article out of 2011, they said that 75% of their users or of their subscribers are actually watching movies that have been recommended to Netflix. So just imagine if it's already 4 years back that 3/4 of their users are already watching the movies that have been recommended to them. The number is quite likely to further rise as well. So you can see recommendation is not only recommendation, it's actually a navigation in the end. They're literally influencing you what you're going to watch. So, okay, we can see that recommenders are quite useful. You can actually really navigate your users what to do. Let's take it a little more back to the basics. Let's look at recommenders with our 3 kids here, Lucy, Bob, and John. So obviously everyone has their own preferences, which fruits they really like to eat. So here in this case, Lucy loves grapes, strawberries, and pears, whereas Bob really likes apples. Then we have John here, who always buys pears, so we are assuming that he really likes pears as well. So what shall we recommend to John? And we can see that, Lucy on the one hand, yeah, what else would John like? What can we recommend to John? And looking at Lucy, she likes pears as well. Maybe because Lucy likes pears, and on top of that, she likes strawberries and grapes. Let's assume John might actually like that as well, assuming that he has a very similar taste to Lucy. So in this scenario, this approach that we have used here is called collaborative filtering. So with collaborative filtering, you go through all certain rules, or seeing like, okay, how many people actually liked these items together, and based on that, then give recommendations to our new customer here, in this case, John. But then on the other hand, what if John actually has a different preference, more in terms of, well, he likes to have something green and sweet. So he could actually like apples as well, because pears and apples are somewhat similar fruits as well. Well, in this case, this would be content-based filtering. So it's more of an evolution based on the collaborative filtering, because, well, with collaborative filtering, you need to start off with a lot of data on the users itself, on the preferences of those, of all the kids here in this case. With content-based filtering, this is enriched by another data source, for instance. So the data source that is being used here in this case is more something like metadata on each single kid itself. So the metadata here in this case with John is, hey, he likes fruits that are green and sweet, and therefore he would like apples. Another good scenario where you can imagine recommenders in is music. Obviously, everyone has their own music taste. There's so many. There are so many songs out there, so many genres, different artists, and so on and so forth. And what music do you want to listen to? What music should I recommend to you? And there are, again, those 2 different approaches: collaborative filtering and content-based filtering. You might have heard of the 2 streaming services, Last.fm and Pandora, and this is a very nice comparison between the 2. So Last.fm is betting on collaborative filtering, and therefore is basing all the recommendations on users' past behavior. With users' past behavior, I mean, okay, which songs you have rated as 5, which songs you've listened to 20 times a day, which songs you've just skipped after 10 seconds, and so on and so forth, which sounds very good, but it sounds also that it requires a lot of data about the user itself. And therefore, the problem that this approach has is a cold start. So when I join this service, how does Last.fm know which artists I like, which songs I would like, or which genres I would like, and so on and so forth? Obviously, it also depends on the time of the day, because in the morning you might want to listen to some hip music, whereas in the evening it's more chilled out. But yeah, it's definitely a cold start. Last.fm doesn't know anything about the user yet, and yet has to give some recommendations what this particular user might want to listen to right now. On the other hand, there's Pandora, for instance, which is more based on the content-based filtering. So Pandora is more focusing on all the characteristics of the items. So in this case, it means, hey, we have this set of thousands, or actually, let's say millions of songs. And obviously, with each song, there is some metadata. Okay, which artist, which genre would it be, which year group could it fit to, or when did it actually become really popular? So something like the 80s music. So if a colleague of mine who's a huge fan of 80s music joins Pandora and happens to listen to one song of the 80s, then automatically all the songs from the 80s of similar genre would be suggested to my colleague then. And therefore, little information is needed at the beginning. It's all about the data that we already have about the songs, about the music, and so on and so forth. This is actually a very short overview of these two approaches, collaborative and content-based filtering. Here you can see where in which platforms each of those ones are being used. And which algorithms are being used as well. What I would like to point out here in this case is with the collaborative filtering, the implicit versus explicit data collection. So with explicit data collection, what I mean by this is you're watching a movie on Netflix and you actively rate a movie 5 stars or 1 star and so on and so forth. But let's face it, how often do you actually rate certain things? You can't be bothered to actually do that. And even though you really enjoyed a certain series, you don't want to give away your taste, for instance. So yeah, explicit data collection would be you explicitly rating something. On the other hand, the implicit data collection is something that I've mentioned beforehand. How often you have watched a certain series, how quickly you finish a series as well, how often you watch a certain movie, or whether you've stopped after 2 minutes, when you're actually watching a movie, or which movie you're watching in the morning or in the evening, and so on and so forth. So this implicit data collection is obviously of big interest to those who want to collect data in general. So let's wrap this module up. What we've done in this module is, well, we've done a short introduction to machine learning, looked more into, well, handwriting recognition, and in this case, Netflix, because, well, let's face it, if it's about recommender engines, Netflix is probably the go-to example as well. Then after that, we looked into the two main approaches of recommender systems, which is collaborative filtering and content-based filtering. In the next modules, we will be going more into demos. The next one will be about targeted marketing, which is similar to recommending, but here in this case, we will keep it as simple as possible, meaning taking the simplest of the simplest machine learning problem, meaning binary classification. So see you in the next module then.